We now take a look at determining the domain for a square root function. Let's consider the function f of x equals the square root of 9 minus 5x. Now, the domain of a square root function is determined a little differently than rational functions. In a square root function, the object that's underneath the square root cannot be negative, right? Because if you have a negative number, that gives you an imaginary number when you take the square root. So we want to determine where this is not negative. In other words, in mathematical language, we want the expression underneath the radical, 9 minus 5x, to be greater than or equal to 0. This here helps us to determine the domain of the function. Let's solve this linear inequality. Well, linear inequalities are solved in a similar manner to linear equations. We begin to solve this by subtracting 9 from both sides, so we have negative 5x is greater than or equal to negative 9. And then we divide by negative 5. This is where the one little rule comes in that pertains to inequalities that makes them different than linear equations. When you divide by a negative number, you must change the direction, or in other words, flip the inequality symbol. This is a property of inequalities, and if you need, go back and review your linear inequalities. That tells me that x must be less than or equal to negative 9 divided by negative 5, or, since negative divided by negative is positive, that means x is less than or equal to 9/5. Again, let me state, when you take a linear inequality and divide it by a negative number, you must change the direction of the symbol. Hence, our greater than or equal to became a less than or equal to. Our domain then consists of all x values that are less than or equal to 9/5. All of these elements are in the domain. So let's write the set notation for the domain of this function. The domain is the set of all x, elements of the real numbers, such that that x value must be less than or equal to negative 9/5. As long as our x value is less than or equal to 9/5, when we substitute that x value into this radical, we will come up with a positive answer, or 0. So this here is the set notation for our domain for this function. Now let's write the interval notation. Let's refer to our number line. Well, 9/5, well, that's just 1 4/5. So when we go on the number line, it's going to be right here, approximately right here in between 1 and 2. This is 9/5. And we want all values that are less than or equal to this. Alrighty, so everything less than will be on this side. And equal to means we're going to fill that dot in. This here represents the set of all x values less than or equal to 9/5. So if we take any of these numbers, they are in the domain of this function. The interval notation that corresponds to this would be all numbers from negative infinity all the way to 9/5. This time we need to include it, so we use a closed bracket to include 9/5 in our quantity. The domain is the interval negative infinity to 9/5, close bracket. Let's take a look at another example. Let's determine the domain of the function w of x equals 1 over the square root of 17x plus 3. This is a little trickier than the last example. This is not only a square root function, but it's also a rational function. So how do we find the domain of this function? So let's first concentrate on the square root part of it. The fact that this is a square root function tells us that what's underneath that square root has to be a non-negative number. But more so, the fact that this is a rational function goes on to tell us that what's underneath can also not be 0. So it's neither negative nor 0. So 17x plus 3 cannot be negative and it can't be 0. That means it must be a positive number only. In fact, it must be strictly greater than 0. It can't be 0 because it's the denominator of a fraction, and it can't be negative because you can't have a square root of a negative number that turns out to be a real number. So the inequality that will help us solve the domain for this function is 17x plus 3 greater than 0. We want to find all x values that will make this equation true. So let's solve. We have 17x is greater than negative 3. X is greater than negative 3 over 17. Because we're dividing both sides by a positive number, we don't have to worry about changing our sign. We just treat this like a regular linear equation. These are our domain values. So in set notation, we would say that our domain is the set of all x that are elements of the real numbers such that x is greater than negative 3/17. This is the domain written in set notation. In interval notation, we want to refer to the number line. Negative 3/17 is part of the way between 0 and negative 1, so let's approximate it right here. So we have negative 3/17, and we want to consider all x values that are greater than negative 3/17. So that's everything on this side. And it's open, it stays open because we are strictly greater than. We cannot include negative 3/17 because that would make our denominator 0, and we can't have that in a fraction. So in interval notation, we would say that the domain is the open interval negative 3/17 to infinity. That's the domain for the function w of x. We finish with one last example. Example 1f, determine the domain of the function g of x equals the square root of x plus 10 over x minus 6. This is by far the trickiest example that we've done together. To determine the domain of this function, we have to consider both the square root function and the fact that this is also a rational function. Let's focus first on the square root part of it. We have the square root of x plus 10, and we know that x plus 10 has to be non-negative, right? It can be 0 because it's in the numerator, and it can be positive, but it just can't be negative. That means that x plus 10 must be greater than or equal to 0. Or if we subtract 10 from both sides, that tells us that x must be greater than or equal to negative 10. That will give us the domain for this part of the function. How about the bottom? Well, in the bottom, we have x minus 6. And because this is a rational function, we know that we can't have 0 in the denominator. So we want to determine all values where that happens. X minus 6 is 0 when, if we add 6 to both sides, x is 6. And we want to exclude this, right, from our domain. So that tells me that our domain consists of two parts. X has to be greater than or equal to negative 10, and also at the same time, X cannot be 6. We use these two statements together to define the domain of our function g of x. First, x has to be greater than or equal to negative 10. And secondly, x cannot be 6. What are we looking at? Well, let me start by drawing a number line. And this will help me to see the actual set of x values that are part of our domain. X is greater than or equal to negative 10. So that means all values that are greater than or equal to negative 10. That's this set right here. All values greater than or equal to negative 10. However, in that set, we do have a number 6, correct? Because 6 is greater than negative 10. That cannot be included. That means that we have to not include 6. So we have an open circle here at 6, right? So the domain is all numbers starting at negative 10. And everything greater than negative 10, but not including 6. Let's write our domain then in both set notation and interval notation. The domain of the function g of x consists of all x elements of the real number such that x is greater than or equal to negative 10 and x is not 6. This would be the set notation for our domain. The interval notation, it would consist of all numbers from negative 10 to infinity, not including 6. So it would be the interval negative 10 to 6, all numbers between negative 10 and 6, including negative 10, and then all numbers that are larger than 6. So the interval from 6 to infinity. Open brackets at 6 because that's not included. This then would be the interval notation for the domain of this function. Alright, that finishes up our examples. I hope domains of functions are a little more clear now. Good luck and have fun with the problems.